Have you ever wondered how organic reactions are optimized? This is the fascinating world of chemical development, where the optimization of organic reactions plays a pivotal role. It's a realm where we strive to enhance chemical reactions, making them more efficient, more cost-effective, and more eco-friendly. Just like optimizing a recipe to get the perfect cake, chemical development focuses on fine-tuning the process of organic reactions. This involves selecting the most suitable synthetic pathways, using the right raw materials and reagents, and controlling the reaction conditions to achieve the highest yield and quality of products. The purpose? It's not just about getting the reaction to work. It's about making it work the best it possibly can. It's about creating processes that are more sustainable, more economical, and safer for both the workers and the environment. As we dive deeper, you will see how this optimization process is a cornerstone of efficient and sustainable chemical production. How do we choose the most efficient path to create a specific chemical? Now that's a question that keeps chemists on their toes. Let's delve into the world of optimal synthetic routes, shall we? The first approach is retrosynthetic analysis. Picture it like a maze. You're trying to reach the center, but from the outside, it's overwhelming. Now imagine if you could start from the center and work your way out. That, in essence, is retrosynthetic analysis. Chemists begin with the desired product and trace their way back to the simplest starting materials, identifying potential synthetic routes along the way. Next, we have the chemoselective approach. Here, chemists use their knowledge of reactivity to select reactions that will occur with only one functional group in a molecule, while leaving others untouched. By carefully choosing reagents and conditions, a chemist can coax a molecule to react exactly how they want it to. Now think about economics. The cost-effective approach involves considering the financial implications of each synthetic route. Factors such as the cost of raw materials, energy requirements, and waste disposal all play a role in determining the most economical route. Then, there's the green chemistry approach. This focuses on minimizing the environmental impact of chemical processes. It encourages the use of renewable resources, energy-efficient reactions, and methods that produce less waste. Finally, we have the pilot plant approach. This is where a small-scale version of the process is tested before scaling up to industrial levels. It's like a dress rehearsal, allowing chemists to identify and address any potential issues before the main event. But remember, the choice of synthetic route isn't a case of one size fits all. It depends on a myriad of factors, including the complexity of the desired product, the availability of starting materials, and the intended scale of production. So the next time you wonder about the journey a chemical takes from raw material to finished product, remember that it's not just a straight line. It's a complex and intricate dance, choreographed by the skillful hands of a chemist. The choice of synthetic route can drastically impact the efficiency and sustainability of the manufacturing process. And that, my friends, is the art and science of choosing optimal synthetic routes. The building blocks of any reaction are the raw materials and reagents used. Now let's delve into the importance of making the right choices in this arena for optimizing organic reactions. Consider raw materials and reagents as the heart of any chemical reaction. They dictate the direction of the reaction, impact the yield, and determine the quality of the final product. Choosing appropriate raw materials is like choosing the right ingredients for a gourmet meal. You wouldn't use stale spices for a high-end dinner, right? Similarly, the purity and quality of the raw materials play a crucial role in the success of the reaction. Reagents, on the other hand, act as catalysts, accelerating the reaction or enabling it under certain conditions. The right reagent can be the difference between a reaction that takes hours or mere minutes. Remember, the right raw materials and reagents can make a world of difference in the outcome of a reaction. What happens when we tweak different variables in the process? Let's dive into the world of process variables and quality control. Process variables are the elements that can be adjusted during a chemical reaction to optimize the yield and quality of the product. These can include temperature, pressure, concentration of reactants, and even time. Think of these variables like the knobs and dials on a soundboard. Each one can be adjusted to fine-tune the outcome, but it's the precise combination of settings that creates the perfect harmony. In a chemical process, adjusting one variable can drastically change the result, sometimes in unexpected ways. For instance, increasing the temperature might speed up a reaction and improve yield, but if it gets too high, it could also lead to undesirable side reactions or degrade the product. Similarly, adjusting the concentration of reactants can impact the rate of reaction and the yield. This is where quality control comes into play. It's not enough to simply adjust variables and hope for the best. We need data, we need analysis, and we need a systematic approach. Quality control in process analysis involves monitoring and testing the product at various stages of the process to ensure it meets the desired standards. This could involve checking the purity of the product, examining the physical characteristics like color or texture, or even using sophisticated analytical techniques to check for impurities. If the quality isn't up to the mark, we can go back and adjust the process variables again. This iterative process of adjustment and quality control is key to optimization. It helps us understand the effect of each variable and how they interact, allowing us to fine-tune the process to get the best possible yield and quality. So you see, process variables and quality control are like the secret ingredients in the recipe of chemical optimization. They allow us to control and predict the outcome, ensuring we get the right product in the right quantity with the right quality every time. Understanding and controlling process variables are key to achieving the desired product quality and yield. What steps follow after a reaction is complete? You might be wondering? Well, let's dive right in. Once an organic reaction has run its course, the workup stage begins. This is a crucial part of the process where the reaction mixture is treated to isolate the desired product. Depending on the nature of the reaction, different workup procedures might be implemented. These could include extraction, distillation, recrystallization, or chromatography. Each of these methods has its benefits and drawbacks, and the choice largely depends on the specific characteristics of the reaction and the product. Product isolation is the next step in the sequence. At this stage, the product is separated from the reaction mixture. This stage is all about purity. The aim is to isolate the product in its purest form, free from any impurities or byproducts. Remember, the goal is not just to make a product, but to make a product that is of the highest quality possible. Now, let's move on to scale-up. This is where the magic really happens. It's one thing to perform a reaction in a small test tube, but it's an entirely different story to replicate that reaction on a larger scale, say, in an industrial setting. This is where planning becomes crucial. It's about considering all the variables, from the amount of raw materials needed to the type of equipment required. It's about predicting and mitigating potential problems before they arise. The optimization of organic reactions is not just about the reaction itself, it's about the entire process, from the selection of raw materials to the workup and product isolation, right through to the scale-up. Each step must be carefully planned and executed to ensure the highest yield and quality of the product. So what have we learned? The journey doesn't end when the reaction is complete. In fact, some might say that's when it truly begins. The workup, product isolation, and scale-up stages are all integral parts of the process. Proper planning for these post-reaction steps is crucial in optimizing the entire process. So let's not underestimate their importance in the grand scheme of things. How can we make chemical processes safer and more sustainable? In the realm of chemical development, we must consider the environmental impact of our processes. The design of environmentally friendly processes is a crucial step. This involves optimizing processes to minimize the production of harmful byproducts, reducing energy consumption, and utilizing renewable resources whenever possible. Effluent minimization and control, or in layman's terms, reducing and managing waste, is another significant aspect. This includes both solid and liquid waste, and even emissions to the air. By reducing the amount of waste produced during a process, we not only lessen the environmental impact, but also improve the efficiency of the process. Moreover, effective waste management ensures that any waste produced is disposed of in a manner that minimizes harm to the environment. Moving on to the manufacturing of active pharmaceutical ingredients, or APIs, there are specific health hazards to consider. These include exposure to harmful chemicals and risk of contamination, among others. Green chemistry approaches are a boon here. They aim to reduce or eliminate the use and generation of hazardous substances. For instance, replacing harmful solvents with safer alternatives, or developing catalysts that can drive reactions more efficiently and selectively, reducing the need for excessive reagents. Green chemistry approaches not only make the process safer, but also contribute to sustainability. They are the future of chemical development, paving the way for a healthier planet and safer working conditions in the industry. How do we handle chemicals safely? The answer lies in the Material Safety Data Sheet, or MSDS. This document provides a wealth of information about the potential hazards of a chemical, its composition, and the precautions required for safe handling and storage. MSDS is a crucial tool for ensuring chemical safety, from proper use of personal protective equipment to emergency procedures. Remember, in the world of chemistry, safety should always be a priority, and MSDS is a valuable tool to ensure it. Let's wrap up our journey through the optimization of organic reactions. We've navigated the vast landscape of chemical development, from the initial selection of the most appropriate synthetic routes to the careful choice of raw materials and reagents. Remember, each decision made in these early stages has a profound impact on the yield and quality of our products. We've also delved into the intricacies of process variables and quality control, highlighting how these crucial elements can shape the course of our reactions. Then, we explored the final stages of workup, product isolation, and planning for scale-up. And let's not forget the vital role of environmental considerations and health hazards, alongside the indispensable material safety data sheets for safe chemical handling. Each step in this process is a cog in a well-oiled machine, all working in harmony to optimize our organic reactions. So stick around for more insightful journeys into the world of chemistry. Subscribe for more because you won't find me later.